Good afternoon, class. So today we start CPU scheduling. We'll talk about basic concepts, scheduling criteria, and scheduling algorithms for processes. And here are the chapter objectives. So we assume a process goes back and forth between CPU burst stages, in which it's doing computation, and I/O burst stages, in which it's performing I/O, either reads or writes. And during an I/O burst, the processor, unless we perform a context switch to another process, is sitting idle. That's something we want to avoid. So when a process enters an I/O burst, the CPU scheduler will perform a context switch to a process that is ready for its next CPU burst. So having several processes that are ready to go at any particular point in time and being able to context switch between them is what is known as multi-programming and maximizes CPU utilization. This chart illustrates that the vast majority of CPU bursts are quite brief, well under 8 milliseconds. Interpolating here, it looks like most of them are in the neighborhood of 2 milliseconds. Thinking back to an earlier chapter, remember that we spoke about three different types of schedulers: the short-term scheduler, which is what we're studying now, or CPU scheduler, the medium-term scheduler, and the long-term scheduler. So it's the CPU scheduler that determines which process will run next. And as mentioned here, the ready queue can be prioritized in various ways that we'll be looking at shortly. The CPU scheduler runs under these four conditions shown when a process switches from running to the waiting state, i.e. when it makes the transition from a CPU burst to an I/O burst. To there, switches from running to ready, which would occur during an interrupt. Switches from waiting to ready, which could be the result of an interrupt if a waiting process is I/O complete. At that point, that process is ready to run, so it'll re-enter the ready queue, and perhaps we want to perform a context switch to it, and finally, when the process terminates. Processes that are allowed to execute until they either perform an I/O or terminate. Scheduling algorithms that allow those processes to continue are termed non-preemptive. If a process can lose the processor, if a context switch can occur while a process is still in the running, i.e. ready state, during its CPU burst, those scheduling algorithms are called preemptive algorithms. Preemptive algorithms are often used in interactive systems. So here we're distinguishing between the actual selection of which process to run next and actually performing the context switch to that process. That's the job of the dispatcher. Here are various scheduling criteria. I'll talk briefly about the last three. Turnaround time can be described as the amount of time that elapses between when a process is created and when it terminates. Waiting time is, you can think of it as its turnaround time minus all the CPU bursts minus all the I/O bursts. And what you have remaining then is the amount of time that the process has been sitting in the ready queue. Response time, there are various definitions. Here you can see one definition. Another definition is the amount of time that elapses between when a process starts and when it produces its first output, which is important in interactive time-sharing systems. Often these criteria can pair of criteria can conflict with each other or bias the system against certain types of processes. So for instance, for throughput, if I want to maximize throughput, I would be looking to run processes with short CPU bursts, which would bias the system against processes that are CPU bound, or in other words, that have very long CPU bursts. Okay, this slide simply shows what we want to achieve with respect to each of the scheduling criteria on the last slide. So for instance, we want to maximize CPU utilization, not minimize it. All right, so here's our first CPU scheduling algorithm, first come, first served, which is just as it says. So in this example, we have three processes, P1, P2, P3, that arrive in that order. And you can see the burst times, presumably in milliseconds listed. So process P1 runs first and runs for its 24 milliseconds, followed by process 2 for its 3 milliseconds, and finally process 3 with its 3 millisecond burst. And this Gantt chart illustrates that. And you can see the waiting time is for process 1, it doesn't wait at all, so its waiting time is 0. Process 2 waits for 24 milliseconds, then it executes to completion, and then process 3 spends a total of 27 milliseconds. In other words, the 24 millisecond CPU burst of P1 followed by the 3 millisecond CPU burst of P2 before it begins to execute. So we have the wait times 0, 24, and 27, giving us an average waiting time of 17 milliseconds. Here you see illustrated that the average wait time depends heavily upon the order of arrival of the processes. In the previous slide, the average waiting time was 17 milliseconds. Here, the average waiting time is 3 milliseconds. So first come, first serve scheduling. The ready queue is prioritized on process arrival time. The next CPU scheduling algorithm is shortest job first. In shortest job first, the ready queue is prioritized on burst length, with processes with shorter CPU bursts being given priority. Of course, the problem one runs into is determining what that next CPU burst will be. In general, that's unpredictable, but as mentioned here, it can be proven that shortest job first gives the minimum average waiting time for any given set of processes. So here's an example Gantt chart, assuming that these 4 processes all arrive at the same time. We prioritize process 4 first because it has the lowest burst time, followed by process 1, followed by process 3, and then finally process 2 will run last because it has the highest, or the maximum burst time. So one way of predicting the next CPU burst is to use exponential averaging. So in this equation here, you can see T sub n is the actual length of the nth CPU burst, and tau sub n is the predicted length of the nth CPU burst. We make use of a coefficient alpha, which varies between 0 and 1, and allows us to emphasize either the predicted value if alpha is closer to 0, or to emphasize the actual length of the CPU burst if alpha is close to 1. right? So this allows us to form a balance between actual CPU burst and predicted CPU burst. And you can see from the way this equation is constructed that, that the predicted value is a function of the predicted value for n plus 1 is a function of all the previous predicted values. And as mentioned in the last bullet, the preemptive version is called shortest remaining time first. And the way that that works is if a process with a shorter remaining time makes a transition from waiting to ready, then that process will preempt the running process and a context switch will occur. So this graph illustrates how exponential averaging works. So there are a number of short CPU bursts. The predicted burst value will decrease, and then if the bursts become long, due to the exponential nature of the prediction equation, the predicted value will begin to rise. I'll skip this slide. All right, here's an example of shortest remaining time first. So we start with process 1 because it arrives at time 0. But then at time 1, process 2 arrives. So at that point, process 1 has a burst time of 7 remaining, but process 2 has a burst time of 4. So that's the shortest remaining time. So process 2 will run. During its run, processes 3 and 4 arrive, but neither of them have a shorter burst time. So process 2 runs to completion. At that point, we pick up process 4 because of the remaining processes. It is a burst of 5, process 3 is a burst of 9, and process 1 still has its burst of 7 remaining. So process 4 runs to completion. Then process 1 will run for its remaining burst of 7 milliseconds, finished by process 3. Then in terms of computing the waiting time, process 1, since the start of its last burst is at 10, its waiting time is 10 minus the burst it had already received, and remember it arrived at time 0. Process 2's waiting time is 0 because it began running as soon as it arrived. Process 3's waiting time is 17 minus its arrival time of 2. And then finally, process 4, its waiting time is the time at which its final CPU burst began minus the 3 of its arrival time. So note that the way we compute these wait times is to find the start time of the last CPU burst, subtract any previous CPU bursts, and then finally subtract the arrival time. Right, assigning processes a priority number that's another way of scheduling by using that priority number to order the ready queue. As mentioned here, the CPU is allocated to the process with the highest priority because that process will be at the head of the queue. We can imagine preemptive and non-preemptive versions of this. So in a non-preemptive version, it's possible that a process with a lower priority is running and will run to completion or until its I/O burst before the process with the highest priority runs. In the preemptive version, it is always the case that the process with the highest priority runs. A problem with priority scheduling is starvation. A process with a very low priority may never get any CPU time. One solution to that is to age its priority, so the longer it's sitting in the ready queue without running, the higher its priority rises until finally it will get some CPU cycles. So here's an example of priority scheduling. Let's assume that all of these processes arrive at the same time, and that the priority function is such that a process with a lower priority number has a higher priority. That's something to watch out for when solving problems of this type. Sometimes the higher priority numbers have the higher priority, but in this case it's the lower priority numbers that have the higher priority. So process 2 here has the lowest priority number, so it's the highest priority process. It will run first, followed by process P5, followed by process P1, followed by process P3, and finally process P4. And I'll leave it as an exercise for you to confirm that the average waiting time here is indeed 8.2 milliseconds. Round robin scheduling, which is often used in time-sharing systems, is simply preemptive first come first serve, or FIFO. As noted at the bottom, if the time quantum Q, which is the interval for which a process is allowed to run before it will be preempted, if Q is large, round robin is simply FIFO, first come first serve, and if Q is too small, then CPU utilization will be low because we'll be spending an awful lot of time performing context switches. Here's an example with a time quantum of 4, so you can see that P1 has a total burst of 24 milliseconds, so it requires 6 quantums to complete its CPU burst entirely, whereas P2 and P3 with bursts of 3 milliseconds each only need a single time quantum. Note that their quantums are 3 in the Gantt chart, not 4, because as soon as they terminate, obviously we can perform a context switch to another process. And note for the first 3 blocks in the Gantt chart that looks an awful lot like first come first serve, because that's what it is ultimately. All right, this slide simply illustrates that the shorter the quantum time, the more context switches are performed. This shows the effect of quantum upon average turnaround time. So here along the x-axis you can see various time quantums for this set of processes and the average turnaround time. So note that round robin often gives good response time, potentially at the expense of increased turnaround times. And as suggested here, typically we don't want processes using up their entire CPU bursts. So typically we expect that a process will perform I/O before it reaches the end of its burst time. So here's a variation on first come first serve scheduling, and that's using 2 first come first serve queues, one for foreground interactive round robin sorts of processes, and then one for background longer running batch processes. And as shown, we could use round robin for the foreground queue and first come first serve, i.e. a non-preemptive for the background and then a preemptive for the foreground. And then in determining how to allocate CPU cycles among the 2 queues, we could use a fixed priority scheme in which any of the processes in the round robin queue have a higher priority, which means if there are always processes in the foreground queue, the background processes will starve. Or we could allocate a percentage of CPU cycles between the between the two queues. So in the example here, we could use 80% of the CPU cycles for the round robin queue and 20% of the cycles for the first come first serve queue. Okay, and this obviously can be generalized to as many queues as you might want, where we put the highest priority processes in the highest priority queue, all the way down to the lowest priority processes in the lowest priority queue. And as long as I've been using this textbook, they've always used this corny joke of putting student processes at the very lowest priority. So we can generalize multi-level queues to feedback queues in which a process can migrate from one of the multi-level queues to another one based upon such things as aging. So if a process isn't getting CPU cycles, it slowly moves towards the highest priority queue, and then processes can be moved to lower priority queues, as we'll see in a moment, if they use up all of their CPU burst. No, I'm sorry, not if they use up all of their CPU burst, but if they use up the entire period of their quantum. So here's an example of 3 multi-level queues with feedback, and note that we can use a different scheduling algorithm within each of the queues. So the highest priority queue is round robin with a quantum of 8. The second highest priority queue is round robin with a quantum of 16, and finally the lowest priority queue uses first come first serve. So a process enters in the highest priority round robin queue. If it uses up that entire quantum, it moves down. If it uses up that entire quantum, it moves down yet again. Well, that finishes this installment of CPU scheduling.